Okay. All right, sharing my screen. Can you see the session 3 thing in your screen? All right.
Yes.
Thanks for the confirmation. All right, so let's when we were ending yesterday's session, I gave you an example about how to solve equations using for loops, right? And I gave you a kind of a assignment kind of thing to do that using to do that the same thing for Klinkenberg's problem to find out liquid permeability given gas permeability. And I also shared a GitHub link where I have already solved that problem. But let me explain that to you so that you have a connectivity with last evening's session, and then we move forward with uh, the libraries part. All right. So let me write this down. Revision. Klinkenberg problem using iterative Newton-Raphson's method. Okay. All right. So I'll copy paste the entire problem statement here so that we can read it, understand what's going on, and then we will solve it using the similar way. To revise what we did yesterday, I have it open with me. What we did was at the end, we tried to find the square root of a number, and we had to basically target this particular algorithm. We had to find out fx, which is everything taken on to the left hand side, and the right hand side should be 0. And the derivative of that function with respect to x. X is whatever value you are trying to optimize. So in this case, we are trying to optimize or trying to solve for permeability. So our x will be changing to k now. OK, so we will be solving for k. Every new iteration, we will be updating our value of k. So whoever does not want to, look at mathy stuff, you can call that x new or x updated is equals to x old minus something. It's just an update rule. Okay, your every iteration you are updating it with something. And what is that something? That something is a ratio of the function at that x. Basically, this is x old. Okay, x is x old. F x old divided by f dash of x old. Okay, so now let me copy this Klinkenberg problem in the code notebook, and we will solve this. Just give me 1 minute. Snipe that up. Okay, copy, paste. All right. So if you can see it, basically, this is the equation that we have, f of kl. Okay, 2.69 kl to the power 0.64 plus pm multiplied by kl minus pm multiplied by kg. Here pm is the, because this is being run on a core sample, pm will be the average pressure, mean pressure across the ends, P1 plus P2 by 2, something like that. Okay, so like you can see equation 3, which is this one, I've copied it from somewhere from my GitHub repository. So this equation can be used to calculate the absolute permeability of liquid when only gas permeability measurement of a core sample is made. And that measurement is made at PM, which is the average pressure. This nonlinear equation can be solved iteratively by using Newton-Raphson's iterative methods. The proposed solution method can be conveniently written as, you can see k new is equals to k old minus fk upon f dash k old. Okay, where ki is the initial guess or whatever, and you are trying to update it recursively. All right, and we will need the f dash k because we already know the fk. Okay, we will have to we will have to differentiate it one time with respect to k, so that we have f dash k, and this is the f dash k with us, and this iterative procedure is repeated unless and until we observe convergence. All right, so this is the procedure or the algorithm. Now what is the problem statement we are trying to solve? Let me copy that as well. What is the problem statement? This is the problem statement. This is the problem statement. The permeability of a core plug is measured by air. I told you yesterday, this problem arises because air has different properties as compared to oil in the reservoir. I know that in wherever I got that core sample from, the original fluid in that reservoir was not air. That was some other fluid with some other wettability properties, right? And liquids normally have no tendency to, stick on the rock surface. They are very wetting. They have more tendency to stick on the rock surface as compared to gases. Gases have no tendency to stick on the rock surface. So every time you measure the gas permeability, the liquid permeability equivalent to that will be a bit lower than that, because gases are free to flow. Liquids, they love the rock, so they stick every time they flow. So that's the simple theory behind it. So one measurement we have available to us, 2.15 to the mean pressure is given, 2.15 to psi, and at that mean pressure, the average air permeability is 46.6 millidarcies, and we need to estimate the absolute permeability of the liquid whichever was present in the original reservoir. Okay, remember, we are trying to figure out something from 10,000 feet deep or whatever, just by pure math using computations, so which is a power in itself. So compare the result with the actual. They have also given you later down the lane, when they actually calculated the liquid permeability using some fancy equipments, they got that to be 23.66 millidarcies. So this is our benchmarking solution. We need to solve this using Newton-Raphson's and find out whether our final solution of liquid permeability is close to 23.66 or not. Okay. So what we will do here is we will ask the user for, uh, we will ask the user for initial guess, because we want to solve our problem at various initial guesses, right? So we want to ask the user for enter your first initial guess of absolute permeability KL. Okay. But even before we do that, how about we first create, just like we did yesterday, right? We created two functions, fx and f dash x. Let's create the same things for this case as well, so that the syntax looks more like a Newton-Raphson syntax. Okay, so let's create that. Okay, so def, this time it will be f of k, because we are now dealing with permeability. Okay, so in f of k, we will need k values. We will need the pm and the kg. Okay, we will need the pm and the kg. Okay, so we will need the k value, which is our current step, whatever value of k there is at the current step. And we will need the value of pm, which we have with us in the form of 2.15 to psi. This is a constant, 2.15 to psi. And we also need what? We also need kg, which is which can be provided from the problem statement or whatever. So let's assume that air permeability is already given to us, which is 46.6 millidarcy. So let's provide it as a default argument. Okay. And what is fk? Fk is this one. This one, 6.9 multiplied by KL to the power 0.64 and so on. So we can return that entire thing. Okay, Fk is equals to 6.9 multiplied by KL to the power 0.64, K to the power. How do you do power in Python? K to the power 0.64. By the way, all this is from Tariq Ahmed textbook, which is a very popular geosciences and reservoir engineering textbook. So you can have a look at that. Okay, so 6.9 multiplied by k to the power 0.64 plus pm, whatever is pm, multiplied by k minus pm multiplied by kg. Okay, all right. So that's fk, and that's what we return. Return fk. Similarly, we have f dash k, def of f dash k. Okay, so what is the formula for f dash k? This is it. All right, you will ask me, is there no way to automate differentiating and stuff? Yes, there is, but we will need to meet for a 1 month long course for that, because that comes in as a part of TensorFlow, auto differentiation and stuff like that. So that is a bit, too far fetched for now. But yes, there is. If you ask me, yes, there is a way to auto differentiate an equation in Python. So that there is. Okay. So again, in this also we will need k as well. we will need PM as well, and we can need we might not need, but just in case if we need, we can also provide 46.6. Okay, I'm providing it as a default argument because these are supposed to be constants. Okay, so f dash k is equals to 4.416. Simple differentiation of this equation. Okay, 4.416 multiplied by k to the power minus 0.36. Okay, plus PM, and return f dash k. Okay, so now what we will do is we will ask the user to provide an initial guess of liquid permeability. And this has like this, you don't have to be very smart at providing that, because Newton-Raphson always converges. Remember, when we were trying to solve for square root of numbers, the initial guesses we provided were absolutely terrible, but still we were able to figure out the final value. Okay, so that was a proof that Newton-Raphson will, more often than not, if you provide the good number of iterations, it will always converge to a solution. Okay, so that's a good thing. So now we can just iterate for I in range. Let's say number of iterations we provided to be 100 only. Okay, so now what we will do is we will update the above value of k equals to k minus fk of what value you need to provide. Remember, in the functions lecture, we talked about how many minimum number of arguments this function needs. Because two of them are default arguments, we only need to provide one value to this. So let's provide it k only. Okay, divided by f dash k and k only. Okay, now we will run this. Okay, we will run this. Enter the initial guess. Let's say initial guess, I don't know what my initial guess. Let's say I provide 2. Let's see whether our k final has now gotten close. So you can see our final estimate of k is 22.84, and we were to compare this with 23.66, which means we did get close. We started at an initial guess of liquid permeability to be 2 millidarcies. Absolutely horrendous assumption. Terrible. It tells us that I have no clue about what my reservoir was, but math helped me in this case. My understanding of Newton-Raphson's method helped me in this case. Okay, now if I repeat this for, let's say, 1,000 iterations, and I provide the same initial guess, press enter. Let's see what is k now. You can see now it is not improving that much, which means even if you went from 100 to a 1,000 iterations, it did not make much sense. Let's see the overall transition from initial guess to the final guess. We can append every new permeability to this list that we have, k underscore dot append k. This is just to track how Newton-Raphson's basically improved the entire thing. Okay, so if I run it to, okay, now what I will do, you don't have to worry about visualizations, but I want to see whether it's transitioning towards a plateau. It's converging, because we are saying that the solution is converging, but what does that mean? So I can import matplotlib.pyplot, which is a plotting library in MATLAB style, as PLT. This is a statement that you will always write. Okay, because this is like calling the powers of matplotlib, telling Python that, hey, I need matplotlib's help in this code. Okay, and then I can do the plt.plot. Okay, k underscore pyplot, sorry. So you can see this is like the 1,000 iterations was like an overkill. If we repeat this only for 20 iterations, let's repeat it only for 10 iterations, let's say, and then visualize the same thing. You can see after the fourth iteration or the third iteration, on the x-axis we have iterations, on the y-axis we have the value of permeability. You can see after the third or the fourth iteration, our permeability value, and let me also plot the original permeability that the question has provided. I can do that by plotting a horizontal line, which is 23.66. I can give it a color of red. So you can see, yes, we are a bit far away, but the Newton-Raphson's method will not get you any further. So basically, there was no need to provide you 1,000 iterations. You could have done that only in 8 iterations only. Even if I did that on the fourth iteration, uh, the Newton-Raphson's method could have just concluded. And I remember from Tariq Ahmed, the textbook, they solved this entire thing in 3 iterations, which means we did not even need the fourth iteration, as is clearly evident from the plot. So this is the basic theory behind a lot of algorithms as well. Even in machine learning, we are trying to find the sweet spot. The sweet spot here is 22.84, 23.66, something like that. And this much accuracy is accepted in reservoir engineering. So the sweet spot could be obtained in this many iterations. People use the word epoch when they do machine learning or deep learning. But the ideal aim is to provide enough number of iterations or training time so that the algorithm successfully converges to a sweet spot. And the enough training time was good enough for 4 to 6 iterations in this case, which means we could have saved our computation power. We did not need to provide even 10 iterations. So now if I repeat this for just 5 iterations and I provide 2. So you can see now if I provide minus 200, let's see whether that works out or not. Minus 200. And I run that. You can see it still works. And now this time it's getting better. Our accuracy is getting better, which means what? If you assume function, the curve of the function, the graph of the function, maybe to the left hand side of the origin, which means the negative x-axis, the function slope is kind of good enough to transit towards the solution really better as compared to the function on the right hand side. Maybe there was a local minima on the right hand side of the origin. So this is where math and our understanding of the solution comes in. But this was just me giving an introduction how you can relate the simple theory with the theory of machine learning as well. Okay, so this is all about Newton-Raphson's. Does anyone have any doubt on how we did that? This is a great application of iterations for reservoir engineers. Okay, you will find your own ways to solve various other problems. But do you understand what I did here? Anyone, any doubts? Please let me know before we move on to the libraries part. Please feel free to type in the chat. I'm taking a 2-minute pause here for any doubts with anyone before we move on to the main thing for today.